Hello everyone, and today we'll be seeing one of the problem from Geeks for Geeks. The problem is pretty easy, but it tests your fundamental so, abilities of implementing few basic standard algorithms, and one of them is a binary search. Let's discuss what the problem says first. The problem is search the insertion point of k in a sorted array. Now we are given a sorted array ARR, zero-based index of the distinct integer and an integer k. Find the index of k if it is present in ARR. If not, then return the index, where k should be inserted to maintain the sorted order. So either we wanted to understand the existing index if it is present at all, but if it is not present, we go ahead and return the insertion index. So in this case, where 5 should be inserted is because it should not be inserted because it already exists. So 0, 1, 2. 2 is the position where it exists. But in this case, 2 doesn't exist, example number 2. And the insertion position can be 1. So 0 is 1. 1 position here we can insert 2 and the array is still sorted. And with 15, we can insert it at the last position and array is still sorted. So there are two methods and I'll tell you both of them. One of the method here is just a simple two-liner thing where we won't go ahead and binary search upon the array and return it. So int x, and where x is the index, we use arrays.binary search a and k. So one good thing about Java is if x is present, then x is greater than 0, greater than or equal to 0, I would say, then that means x is already the k is already present and the index is x. But if not, we get the insertion position out of the box, which is -x, -1. So I'll quickly submit this and test it. Yeah, it has been submitted, but the problem doesn't want us to use the standard functions. If we use them, what's the point of learning? That's a good thing. So we'll not go ahead and use this. I'll just comment this out and I'll use the naive method, or I'll go ahead and implement this. So for implementation, how can we solve this problem? Let's understand. Let's break the problem where we want this example and we wanted to know the insertion point. We already know how to understand the problem when we already have either of the element present within the array. So now here k is 2, we don't have anything within the array. So how can we go ahead, how can we solve this problem? So we can take an advantage of the arrays sorted, so we can have L and R. We know that at any given point of time that my k would be within the limits of L to R, right? Correct. So now given this L and R, we wanted to know where k as 2 can be inserted. So I'll break this array into half. It's very similar to binary search. In fact, we are implementing binary search, and in the next iteration my R would shrink down. So L is at this position, R would be also L is, let me take it down, 0, 1, 2 and 3. These are nothing but the indexes. So yeah, 0 plus 3 is 3, 3 divided by 2 is 1, so R is at this position. In only one step, we have reduced the array from this size to only 2 elements. So this is the power of binary search, and this is what they want us to go ahead and implement log and time complexity. So cool. Going further, we understand that hey, L and R, and we want k is equal to 2 again. So how are we going to go ahead? Once with this L and R, what would be my next mid? The next mid would be 0 plus 1 divided by 2 is 0. And now I wanted to understand, can I move further? Can I move further? And next, how can I decide? It would be decided by L and R. So if L and R are in the valid positions, then only I can say that hey, I can move forward, else I cannot move forward. That means prior to jumping, I wanted to understand the best values for L and R. And frankly, within L and R, do I really want R? Means take a wild guess that hey, if I'm having an R and if I wanted to update an R in such a way that L and R would be L is equal to med plus 1 or R is equal to med minus 1, do I really want R? Because R is the extreme limit. I know if K is 2, K won't go beyond R, and that's the case. We don't even want R, we just want L. With that thing in mind, I know if this is still confusing, hold on for a while and things will be more clear as we implement the solution. So int L R a dot length minus 1, both are indices, and sorry, and while I'm running for L is lesser than or equal to R. Now obviously I'll get a mid, int mid is equal to L plus R minus L divided by 2, and now I'm checking that hey, if A of mid is equal to K, then hey, we have hit a jackpot and it is an element which is already present, and we return mid. Problem arises when difficulties come when you don't have that, and if you know that mid element and K is not equal, then there might be a relationship, either it is greater or it can be a lesser element. So if it is a greater element, we know that we need to lower the number or search in lower parts of the array. Because why? Because our array element was greater and we wanted to search in the lower part. That means we wanted to shrink R, and that means mid minus 1, and similarly left is equal to mid plus 1, vice versa. We are expecting to be a greater numbers from the array, and ultimately we will go ahead and return L. Cool. Let's check this for sample test cases, whether it solves it or not. Cool, it solves the problem, and let's try to submit this one. It was the very basic binary search implementation. Why does this solution works is because we don't have multiple repeating elements. If we had a multiple repeating elements, our program would halt directly at this point. If you wanted to still know that how can we deal with elements or what a binary search is means, and click the video on your right, and I'll see you in the next one.